We learned about Aries as the main crash recovery algorithm. The power of the Aries is in its second step, where it repeats the whole history. This, combined with the fact that Aries does not try to work with physical objects only, gives it the power of being used for a wider set of operations. This means that it works with operations as they were done originally, and it does not deal with only healing the results of the failure on a specific media or a physical resource. There are other algorithms that also employ this approach, but limit the redo phase to only the non-loser transactions. Aries, due to the redo of the complete history, and then performing an undo, and using of the CLR logs for its undone transactions, is able to support more diverse set of logical operations. Other alternative approaches include a solution from original system R that uses a page table for mapping pages to disk addresses. It keeps a copy of the changed pages, calling them the shadow pages. The entry in the page table for the transaction performing the change is then updated to point to the shadow page, while other transactions keep seeing the original page. Aborting a transaction discards the shadow page, and committing it results in replacing the original page with the shadow page. This scheme is limited to the physical resource recovery. It fragments data, needs huge storage to perform, and does not yield high concurrency. By far, we discussed transaction recovery and crash recovery. Remember, when talking about failures in the database management systems, we said storage can also fail, and we have to design mechanisms to recover from that as well. Most of the media recovery algorithms work through periodic copies of the database to another backup location, so that we have an extra copy if the media we are working with fails. However, one problem is that copying, especially if we copy the entire media, is a time-consuming operation and will keep the database management system from its main job. So, what is the solution? Remember fuzzy checkpointing, allowing us to save the state of the system while the system is working. We can employ a similar approach here. We use a recent complete checkpoint of the system together with a copy of the database object. Then we use the logs to arrive at the copy of the database object at the time of the media failure. To enhance user experience and minimize the downtime, we can use an approach called high availability. In this approach, we implement two systems in parallel. The one that is currently in use is called the primary, and the one that is not in use is called the backup or the secondary. The backup is usually at a remote location so that it can help in the event of accidents involving a geolocation. It is kept synchronized with the primary through a copy of the database and logs. When a problem happens in the primary system and it crashes, high availability needs a mechanism to detect the failure, at which time it transfers the control to the backup system. The backup system applies the most recent set of logs and recovers the system and starts normal operation. This removes the time that it requires for the system to come up after a crash and start from the failure spot. To make the system even more responsive and the high availability feature even faster, a hot spare configuration could be used. In hot spare configuration, the backup system is in close sync with all transactions, applying log records as they happen. the time of reaching the same state in the system is even shorter because it only needs the undo of aborted transactions. When the primary recovers, the system either transfers the control back to primary or decides to switch roles. This depends on the configuration.